Welcome to the HyperX Academy. This video gives you a high-level introduction to how HyperX handles composite sizing. We'll look at key concepts, the overall setup process, and the main workflows available. Be sure to watch our other composite videos to learn more about specific topics in more detail. When we talk about composite optimization in HyperX, we are referring to selecting the right ply material, laminate thickness, angle, and stacking sequence for your structure. The goal is to balance performance, like weight, stiffness, and strength, with manufacturability. HyperX evaluates each of these variables as part of the optimization process. There are a few different workflows for sizing composites, but they all follow the same general structure. 1. Define the composite materials you want to use. 2. Create a design property that includes your structural concept, the selected material, and any fabrication rules. 3. Set up an analysis property with composite strength methods. 4. Define a load property. And 5. Assign everything to the zones in your model and run the sizing routine. We'll take a look at the first 3 steps because those are unique to composite materials, while steps 4 and 5 are the same for every sizing process in HyperX. Let's start with material definitions. Everything begins in the composite materials library. HyperX includes definitions for both tape and fabric materials. Each entry contains temperature-dependent stiffness properties, which define how the material behaves under load at different temperatures. You'll also see lamina allowables, used in ply strength analysis, and laminate allowables, which apply to laminate level failure methods. If we open Collier tape, we can see these properties in action, along with multiple analysis properties and drop-down menus that provide extensive material definitions beyond most standard FEA processes. There are also correction factors available for advanced sizing controls. Those are covered in a separate video. For now, just know that every aspect of composite materials in HyperX is temperature dependent and able to be corrected to properly match your requirements or test campaigns. And this entire process will be the focus of its own video later on. Next, we move to design properties. This is where you choose the cross-section concept and how the material gets applied to your structure. You can pick from concepts like unstiffened panels, 2 or 3 stack sandwich panels, and stiffened geometries like I-sections, Z's, and hats. There are also optional constraints you can apply, such as ply angle percentages to control orientation balance, layup rules to ensure symmetry or balance, and fabrication rules that enforce full structure plies at the OML, IML, or midplane. These rules help guide the optimization process to ensure manufacturability is factored in from the start. The analysis property includes strength methods tailored for composites. You can choose ply-based or laminate-based failure methods depending on your program requirements and how you've defined your material. HyperX also supports other methods, such as sandwich and crippling analysis methods that incorporate composite behavior. HyperX offers 3 main sizing workflows for composites. The first is preliminary sizing. Preliminary sizing uses either rapid sizing or detailed sizing with effective laminates. Both options provide quick sizing routines to support early-stage trades. They focus on ply percentages and thickness, but neither will result in a full stacking sequence. Both are also good inputs to more detailed sizing in the next 2 workflows. Laminate family sizing builds a set of discrete laminates from a shared stacking sequence. This results in each zone having a specified layup. From here, HyperX can automatically sequence these layups into a global ply layup scheme, which can be communicated directly to your designer. This process using laminate families is our recommended sizing approach because it inherently balances weight savings with manufacturability. Orphan laminate sizing gives you the same fidelity of results as laminate family sizing, but the results are inherently less manufacturable since each zone's resulting layup is not selected from a laminate family with a common stacking sequence. This option is carried over from legacy hypersizer workflows and is typically not recommended. Here's a quick comparison. Effective laminate sizing is fast and great for trade studies, but does not produce results detailed enough for final design. Laminate family sizing provides discrete, manufacturable results with high performance. Orphan laminate sizing provides discrete results that are performant but generally not manufacturable. Note that this table compares initial sizing results using the three approaches. If you were to take the last two approaches all the way through to the global ply sequencing step, the laminate family solution will likely be lighter and easier to make than the orphanate laminate solution. And that's it for composite sizing. Thanks for stopping by the HyperX Academy.